Hello, this is the next video in a playlist that I'm calling Introduction to Probability and Statistics, Illustrations with R. We're in chapter 1 called Probability. And before I start this video, I want to go through some examples to illustrate that people use statistics, but they may not realize they're using statistics. Even p-values, people calculate p-values intuitively, but they don't know they're called p-values. So let's go through some examples. So the first one is when you're cooking pasta, we make, we sample a noodle, so we have boiled water, we throw in pasta, spaghetti or macaroni. It boils for a while and we want to know if it's done. So we sample it. We take one noodle, we eat it, and then we make an inference towards the population, the rest of the noodles. So we're assuming that the population's homogeneous, that this one, that our sample is representative of the population. I mean, everyone has done that. Now, the next one is flipping a coin. Notice that we've only ever observed heads and tails, so we consider them the only two possibilities. But we've all taken a coin and stood it up on edge and balanced it on its edge. So why isn't there three possible outcomes when you're flipping a coin? Well, here we're using empirical results. We've only seen heads and tails, so we don't consider the possibility of it landing on edge. And so the probability of that event is so small that we ignore it. And when we ignore it, our results still represent in reality what happens. Another one is before the start of a game, we might estimate the probability of a team winning. This is called subjective probability. Based upon your knowledge of the team or the sport or the game, you can make educated guesses of the probability of a team winning. Now, in a game next example, in a game that uses a die, we just know that the probability of each outcome of a roll is 1/6, right? That's called classical probability. We know there's only, for example, one way that a 2 can be rolled, and there's 6 possibilities. So we know that the probability of rolling a 2 is 1/6. That's called classical estimation or classical probability. Now here's a silly experiment that I always use to illustrate that everybody uses p-values. They just don't know they're called p-values. And if p-value is an unknown term for you, we'll cover that when we get into hypothesis testing later down this list, the videos list. So it's a silly experiment. I have two coins. I have one coin with two sides, and I'm not going to tell you what's on each side of the coin, but I will flip it and tell you the outcome observed. And your task is to tell me what is on both sides of the coin, right? I'm like, all right, go. And you might say, well, we need to start flipping it. I'm like, okay. So I flip it once and a head lands. And I ask you, what's on both sides of the coin? And most will go, well, we don't know. We've only seen one outcome. Let's flip it more times. So I flip it 3 times and there's 3 heads. What's on both sides? And you go like, well, that's probably not enough. If it's a fair coin, meaning has one head and one tails, the probability of observing 3 heads is still, it's reasonable. It could happen. So right there, you're calculating a p-value. So what if I flip it 10 times and we observe 10 heads? A lot of you will start saying, well, that's starting to be pretty good evidence that maybe it's a two-headed coin. There's not a tail and a head on each side. What if I flip it 1,000 times and we observe 1,000 heads? Now this is where you go, well, if it were a fair coin, one head, one tail, the probability of observing 1,000 heads and 1,000 flips is so small, we have to discount that hypothesis that it's a fair coin. Because anyway, you just calculated a p-value there. But if we assume that it's a two-headed coin, a head on both sides, well, the probability of observing 1,000 heads is 100%. So therefore, we're going to conclude that it's a two-headed coin. Anyway, so we just kind of intuitively calculate p-values. Now, over the next few videos, we're going to develop notation and nomenclature and, etc. So we'll go slow. Definitions of population sample. The overall groups or objects about which we make conclusions or drawn are called the population. The population size can be finite or infinite. A subset or a portion of the population is actually obtained that is used to draw conclusions about the population is called a sample. Definition of subjective probability is according to the subjective or personal interpretation of probability. That's the probability that a person assigns to a possible outcome. Relative frequency interpretation. This is if the experiment can be repeated multiple times. We assign a probability to event A as the number of times that the event occurred over the total number of times it was conducted. Now, a quick illustration in R of this. Let's assume we have a weird 7-sided die, and so the outcomes are 1 through 7. We assign probabilities to each outcome of 1/7, 1/7, 1/14, etc. Now, these would be unknown in reality, so this is just a simulation. We're going to roll the die 50 times. We're going to look at the outcomes. So that we use the sample function in R to sample, the numbers 1 through 7 with these die probabilities. And then let's look at the outcome. So the outcome is we rolled a 1 6 times, a 2 7 times, a 4 3 times. And these are the probabilities associated with it. So we assign the probability of observing a 4 as 6%. And this is frequency estimation or frequency probability. If we were to do an experiment 22 times on a normal die, so 1 through 6, these are possible outcomes that could happen. We observe a 1 4 times, a 2 1 time, a 3 4 times, a 4 7 times. And these are the proportions that we observed it. So we would assign the probability of observing a 4 as 32%. Okay, so already you can see that frequency probability, frequency interpretation of probability is not always very accurate, but it can be shown that the larger sample size you take, the more accurate these frequencies are to the true probabilities. Now, a classical interpretation of probability is if it's all outcomes are equally likely, we assign the probability of event A as this. It's the number of ways event A can occur divided by the total number of outcomes. And so previously we used that like if we had a fair 6-sided die, the probability of rolling a 2 is, well, there's only one way that we can roll a 2 out of the 6 total outcomes, so it's 1/6. So the probability of rolling a 2 is 1/6. And so here's a little illustration of Powerball. And now some of this, this is called combinatoric, so it's 69 choose 5. We're going to review that, I think, in 2 videos, what that notation means. But this is really the classical way of assigning probability to winning Powerball. And so in Powerball, you have 69 numbers, and you pick 5 of them, and the 69 numbers are on white balls. So we say we pick 5 white numbers or 5 white balls that we think are going to turn up. And then the Powerball are on red balls, and there's 26 red balls, and so we pick one of those. So the number of ways to choose 5 white balls, the correct 5 white balls, and the correct red ball is 1 out of this big number. So it's one way out of 292,201,338. So that's a 0.0 with 8 zeros and a 3. That's the probability of winning the grand prize in Powerball. But we can go through each of these. So the probability that we match the 5 white balls and we do not match the red Powerball is 25 ways out of the 292 million. Right? The 25 ways occur Well, there's only one way to match the 5 numbers. That's match the 5 numbers. But since there's 26 possibilities of the red ball, and there's one way to match, that means there's 25 ways to not match. So that's where the 25 comes from. And it's still pretty small. It's a 0.07 zeros and 8. And then we'll just go through these sort of quickly. The probability that we match 4 white balls and 1 red ball, well, there's 302 ways for that to happen out of the 292, so we assign it this probability. The probability that we match 4 white balls and no red balls is there's 8,000 ways for that to happen out of the 292 million. The probability that we match 3 white balls, 1 red ball is 2,160 ways over the 292 million. 3 white balls, 0 red balls, 504,000. So that's 0.1%. Probability that we match 2 white balls and 1 red ball is 416,640. And again, we're going to go over these combinations notation in a couple of videos. Oh, and I always post the R code in the comments if you want it. So we just keep going. 2 white balls, 0 red balls. There's 1 white ball, 1 red ball is 3 million. 1 white, 0 red. 79 million ways that can happen. 0 white, 1 red. 7 million ways that can happen over the 292 million. 0 white, 0 red. It's a 65% chance that you don't match anything. That's crazy. Okay, so I'm at 11 minutes. I'm going to stop the video and we'll pick up on the next one. Thank you so much for watching. I've enjoyed this. I hope you did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.